Hello, welcome. My name is Andrew Richards. I'm the founder and CEO of Codeplay. And what I'm going to talk to you about today is building a custom RISC-V chip to lower the power and cost of GPUs for AI and HPC. So a quick background to vector programming. So in processing, we have something called SISD, single instruction, single data. That's what a CPU does. You have a single instruction and you operate on a single bit of data at once. And then we have something called SIMD, single instruction, single data, which gives you a single instruction and multiple data at the same time. And then that's kind of vector programming. So what that's used a lot for in computer vision, AI, and HPC applications, because you can process lots of data very efficiently. Now, what we find is in real software, you want to have a mixture. So some stuff you want really fast single instruction, single data processing for latency sensitive stuff, like setting things up and allocating memory and controlling, compiling stuff and things like that. And then what you want is bulk vector programming, single instruction, multiple data for processing large amounts of data like you do in AI and HPC. So what we can do is we can have a heterogeneous system which mixes both types of processor in the system, and we can offload all of the data-intensive code from the CPU to the GPU or the vector processor for vector processing. Now I'm going to show you a demo of us doing that. So here's a simple vector add sample written in the SYCL programming model. So the SYCL programming model, it's very like CUDA, it's a very C++ model, but what SYCL does is it's a data flow model that allows us to offload the vector operations. You can see the vector operations in green here. It allows us to offload that vector operation in the green arrows to, in this case, an Intel GPU, and everything's going to run and everything else is going to run on the CPU where it's going to be faster. And we've got this data flow model, which is allowing us to manage the data. So SYCL is an industry standard. It's quite widely used in especially high performance computing. Okay, so I'm going to show you a simulation of running this. Actually, it's not a simulation. This first one is actually going to run for real. So what we're going to do is we're going to use what's called the ICD, installable client driver, to be able to say we're going to use the Intel OpenCL to run the code, and compute CPP is Codeplay's SYCL implementation. There's multiple SYCL implementations, but we use Codeplay's one here, and we offload that vector work to the Intel GPU, and you can see the results are correct. There's not much I can do with a vector add, but at least it gives you a simple example. Okay, so now I'm going to run exactly the same source code. This is exactly the same source code. I'm going to offload that vector add. Instead of to an Intel GPU, I'm going to offload it to a RISC-V processor, which we simulate using the Spike simulator. That's a standard simulator you can use for RISC-V. And we're going to use the RVV vector instructions on that RISC-V core. So it's very performant at doing the vector add. You can configure this core to do all sorts of different things, different kinds of processor, vector widths and sizes and different kinds of memory and stuff. But I'm not going to show that today. I'm just going to show you it running. So here we go. We're going to tell the ICD to switch to RISC-V because we want to execute it on the RISC-V. And now you can see we use the Compute-Auto product from Codeplay to offload that work to the RISC-V simulator based on Spike. And you can see exactly the same code. It runs in exactly the same way. Okay. If you want to have a look at the instructions, here's a simplified version of the RISC-V instructions. As you can see, we're using the vector instructions in RISC-V. So we vectorize that loop. That's something that SYCL and OpenCL does. We vectorize that loop. It's kind of simplified version of it. There's all sorts of optimizations we could do, but you can see it here. And then on the right, I can show you that actually, because we're running on a simulator, we can actually trace through the instructions executing on the simulator, so you can see how they can execute. So you can work out how to design a processor core that's going to do this code in the right way. Okay, that's it.